This video is for Math 116 to talk about the project. So the project has to do with exponential functions. So just a quick review about exponential functions. When you have linear functions which are proportional, you get a straight line graph. You can have a polynomial relationship like a parabola, and that is a curved relationship. It's no longer linear. Now, what happens when you put the variable in the exponent is that you get these exponential functions which grow very quickly. So these are ideas that were, I think, being explored by European mathematicians in like the 17 and 1800s. Well, actually, it was mostly in the early 1800s that people were talking about these ideas. But in any event, in Math 111, when we talk about these ideas, I point out that almost nothing in the natural world can grow like this. Okay? There is almost no example that I know of unimpeded exponential growth. Okay? Because growth depends on resources. And as these things grow, then they consume more and more resources. And so as a result, what you get is what's called the logistic relationship, is that this is really not useful in application. A French mathematician named Pierre Verhulst modified this so that after that initial exponential growth phase, you have a phase where the growth tails off and stabilizes. Okay, and I did a talk about these ideas, I don't know, 10 years ago or something, and I used examples for population growth of places where that are geographically constrained, like England or Rhode Island or New York City, Manhattan Island. So those places are geographically constrained, and their population growth looks something like this. You know, it's actual data, so it's a little bit messier, and it tends to actually hit a peak and then drop off again. But this is much more realistic than this. Now, that's not to say that these exponential functions are not useful to model the natural world. But what's really useful is the negative exponential, right? When I put that negative sign up with the x, that's going to reflect this over the y-axis, and you're going to get a graph that looks something like this. This piece right here, that is actually very important in modeling, let's see here, radioactive decay. Cooling, which is the first question on the project, and medication in the bloodstream, which is the second question in the bloodstream. And the reason for this is that these have to do with probability. There's actually an activity that I do sometimes in class with dice that shows how this decay process has to do with probability. Cooling has to do with the interactions of the molecule in the object with the molecule in the environment, and those interactions are governed by probability, how they run into each other and interact. Same thing with the medication in the bloodstream. The way that it's metabolized is that it runs into metabolites in the bloodstream in a probabilistic way, and so as a result, this, what I call the exponential tail function, is enormously useful in applications. Okay? So that's what our project is based on. We're going to be looking at this exponential tail. Frequently it's going to zero. With the Newton's law of cooling, what you get is you get this ambient temperature T sub A here, and then you've got the initial temperature. Let me see what variable I used. Oh, right, the initial temperature is actually going to be T sub A plus C. Okay, and let's take a look at, I've got a couple pages here that I posted up on the course website on MyOpenMath that talk about solving a Newton's law of cooling problem. So I'll go over one of those and then we'll talk about the second problem. All right, let's see here. So this is the first page of that PDF that I posted along with all of those resources for the project. This is page 178 from my Math 111 textbook. And we've got this standard Newton's law of cooling formula, T sub A plus CE to the minus KT. Okay, so T sub A is the ambient temperature. The value of C depends on the initial temperature of the object. It's the difference between the initial temperature and the ambient temperature. And then this variable K determines how quickly or slowly the object returns to the ambient temperature. Okay, so let's see here. The example, we've got a bottle of soda at room temperature, 72 degrees, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. So somewhere along here maybe is 44 degrees. After half an hour, the soda has cooled to 61 degrees. So let's say, we'll put 30 minutes on here. Then we know that that's going to be 61 degrees. We know that we've got a point right there. What is the temperature of the soda after another half an hour? So after 60 minutes total, what is our temperature going to be? So T of 60 is what we want to find out. Okay, so let's see here. The ambient temperature, T sub A, is given in the problem. We've got 44 degrees there, CE to the minus KT. And I mentioned that C is the difference between the initial temperature and the ambient temperature. So you can just subtract to find that. Looks like it's going to be 28. E to the minus KT. And that conclusion comes from the fact that at T equals 0, the temperature is 72. So you can plug that into our formula. Let's see here, 72 equals 44 plus CE to the minus K times 0. So this is the nice thing about that T equals 0 piece, is that this is going to be e to the 0 power, which is 1. So 72 is 44 plus C, and so C, like I said, is the difference between the ambient temperature and the initial temperature, and that should be 28. Okay, so we've got that. Now we need to calculate the value of K, and then we'll have a formula. Okay. All right, so to calculate the value of K, we'll take this point right here, where T is 30 and the temperature is 61. Let me make sure that we're doing T in minutes here. Okay. Yeah, so I used 30 minutes in the example. You can choose to use hours. So long as you're consistent. This would be 0.5, this would be 1. That's fine too. That's not going to make a whole lot of difference. But I'm going to do this with minutes. Okay, so now we know that we've got a temperature of 61 degrees. We know the C is 28. E to the minus 30 minutes, and then the K. All right, and the goal here is to solve for that value of K. And this measurement of the temperature after 30 minutes will allow us to find a value for K. All right, so let's go ahead and solve this. Minus 44 on both sides. So what's this going to be here? 17. 28 e to the minus 30k. The goal is we want to isolate this e to the minus 30k piece. So that's what I'm doing. I'm subtracting the 44. Now we're going to divide by 28. 17 over 28 is e to the minus 30k. All right, this is where it gets a little bit tricky. You may or may not have done this before, but this is the process for bringing this variable down out of the exponent. Okay? The base of our exponential expression here is the number e, and so as a consequence, we're going to take a natural logarithm on both sides. Okay? The reason why we do that, and it's no different really than subtracting on both sides or multiplying on both sides. If we take a logarithm on both sides, we can use this property of logarithms that says that ln of b to the x power equals x times ln b. And this is just a restatement of one of the properties of exponents, because a logarithm is an exponent. Okay? And that property of exponent says when you raise a power to a power, you multiply those powers. And so that's what's happening here. This ln b is a power, the x is a power, and so in the end, we can actually just multiply them. Why am I talking about this? Because down here, that allows us to bring that negative 30k down out of the exponent, in front as a coefficient. Okay. Now, this is the beauty of using the natural log of e. ln of e is 1. Okay, we can talk about that conceptually. You can confirm it on your calculator, but for the moment, I'm just going to solve this equation. ln of 17 over 28, I'll leave it alone for a minute, and then just divide on both sides by negative 30. And so the value of our constant k is going to be this ln 17 over 28 divided by negative 30. Now let's make a good approximation for that on the calculator. And be careful with your parentheses here. So ln 17 divided by 28, and then I'm going to divide that by negative 30, and that'll give me 0.01663, let's say. Okay, so now our formula is 44 plus 28 e to the minus 0.01663 times t. So there's our formula, and then to answer this question, all we have to do is plug in 60 there. Okay, and let's go ahead and calculate that. Oh, let me show you this one calculation first. Okay, so there's the ln 17 over 28, and then I divided that answer by negative 30. If you calculate that all at once, you might run into some challenges with the parentheses, but that's up to you. All right, so now I'm going to calculate this temperature, 44 plus 28 e to the minus 0.1663 times 60. All right, so let's see what we get here. 44 plus 28 e to the minus 0.01663 times 60. Oh, let me get this going here again. Negative 0.01663 times 60. And so that says the temperature should be about 54. 54.3 degrees. And so there it is. Okay, so there's a calculation, gives us a good approximation for that temperature after 1 hour, 54.3 degrees. Okay, and so that's what I'm asking you to do on the project. Here, we've got an ambient temperature of 70 degrees. We know that T equals 0. The temperature of the coffee is 205 degrees. And then we've got a point in the middle here. After 10 minutes, the temperature is 170. So, I want you to go through this process. with this problem for part 1, and then find out how long this is going to take. So in this one, what you've got is a T of 60. So I gave you a 60 and asked you for a temperature. On this one, you're given a temperature, and I asked you to solve for a time. So let me show you an example of that based on this problem. Okay, just so that it matches up. So let's say, well, we know after 1 hour it's going to be 54 degrees, right? So at T equals 60 minutes, the temperature was 54.3 degrees. Well, let's find out when it goes down to 50 degrees. Okay, so we set our temperature equal to 50. And it's very similar to what we did to solve for K, because the T is up there in the exponent as well. So we subtract the 44 on both sides. 6 equals 28 e to the minus 0.1663 times T. Divide on both sides by 28. So that's going to be 3 over 14 e to the minus 0.1663 times T. And then this is the point where we want to take a natural log on both sides. So ln 3/14 equals negative 0.01663 T times ln E. This is 1. And so we just need to divide on both sides by negative 0.01663. And then we want to get a good approximation for that value. So let's see what we get here. ln 3 divided by 14, and then we're going to divide that by negative 0.01663, 92.6. Okay, so that says it's going to take about another 30 minutes to decrease by 4 degrees and get down to 50. Okay? And that's pretty typical of these. Notice that in the first 30 minutes, it cooled off by 11 degrees. Then in the second 30 minutes, it cooled off from 61 to 54, 7 degrees. And then in the third 30 minutes, right, it cooled off only 4 degrees. Very, very typical of these exponential relationships, okay? Most, and I often draw this in an exaggerated fashion, something like this. Most of the loss of temperature is coming in that part of the curve, okay? And then once it gets here, then it's basically cool. It's cooled off. You know, it's sort of like a cup of coffee. You know, this is the point where it's too hot to drink. Then you got to start drinking it here, because if you wait much longer, it's just going to get lukewarm and not be very delicious. Okay, so that's part 1 on the project. Let's take a look at part 2. So this is medication in the bloodstream that follows that same exponential tail shape. And this also comes from my college algebra textbook. Let's see here. So I'll go over this problem and then talk about how it's related to part 2 on the project. So this one says we've got a function a of t equals 200 e to the minus 0.014 t. Okay. Gives the amount of medication in milligrams in a patient's bloodstream t minutes after the medication has been injected. So we've got minutes on the x-axis and milligrams on the y-axis. Okay. Find the amount of medication in the bloodstream after 45 minutes. We know it's going to start up at 200. And let's see here. So let me make a graph for this. 200 e to the minus 0.014x. You have to use the x on the graphing calculator typically, otherwise it gets really confused. And then you have to go into the table, you have to go into the window to make sure that you can see the graph. So I'm going to go and make my y maximum 200. Y maximum is 200. And I've got 40 as my x maximum. I'll just leave that and see what it looks like. Not quite enough. Let me make let's look at 3 hours, so 180 minutes. Let's see what that looks like. Yeah, much better. Okay, so we get a graph that looks something like this. So let's see here. Find the amount of medication in the bloodstream after 45 minutes. You can just plug a 45 into here to calculate that. That's pretty straightforward. How long will it take for the amount of medication to reach 50 milligrams? So you can do this algebraically, right? You can set it equal to 50, and you can solve this for t. But on this one, I don't ask you to show this solution algebraically, because I've already seen that in part 1. In part 2, so I've said, after you find the values for A and K, make a graph and to show that, and then, we want to know when is it going to reach 10 milligrams. Okay, so to do that, and this problem we want to know when it's going to reach 50, which is right here. So the trick here is to go in and graph this, and put the x in there, and then graph y2 at 50, and then go and find that intersection point. Okay, and we can do that by finding an intersection on the calculator. So let me show you what we're doing here on the calculator. Okay. So there's the original function. Now we're going to go down and we're going to graph y equals 50 along with it. And there it is. And if we just find the x value of that, then we'll know what matches up with 50. So to do that in the calculator, this trace button right above it, it says calculate. So if you go second trace, it'll bring up that calculate menu. Choice number 5 is find the intersection. You can arrow down to it and hit enter, or you can just hit 5. So now it's going to ask first curve, second curve, and guess. So what it's saying is which 2 curves do you want to find the intersection for? I've only got 2 curves on the graph, so I'm just going to say, yeah, that's the first one. Yeah, that red one is the second one. Guess is if there's 2 different intersections around here, then you could move close to the one you're interested in. We're already close to the one that we're interested in. There it is, 99 minutes. Okay. And the graph software has a similar function. If you're working with the graph software and not sure how to find intersections with it, let me know and I'll be happy to help you out with that. So what we're seeing here is that t is 99 minutes. Okay. Now, the problem in part 2 of the project is a little bit trickier because I don't give you this 200. All right. Instead, I give you 2 different points on the graph. So in these examples, normally I've given you the initial starting point and 1 other point. In this scenario, what I've given you is 2 points out here, and I'll leave it at that for right now. And like I keep saying, if you start working on this and you run into questions and you're not sure what to do, let me know. I'll be happy to talk with you about it. So that's it for project 1. Let's see, we'll have a second project to do in a couple of weeks, and that'll be due at the end of the term. So, hopefully this was helpful for you, and as always, if you have any questions, please let me know. Thanks.